So in the last class, we discussed about uh, the TCP topics, different parameters of TCP, and followed by this, today we have one more lab left. Will continue the same lab, the DNS IP relay. The centralized DHCP. So we'll see how the DHCP relay works, and followed by that, we got one more use cases still pending, that is congestion control. So that's by this weekend we will definitely cover that, because we want little more variations, and other topics has to be combined together. So the plan is to combine those two topics together to explain better. And then followed by that, so today the major concentration is for broadcast domains and collision domains, and what is ARP table and what is CAM table. We are not just doing that. We have an use case where we troubleshoot, and we'll see the difference of CAM table and ARP table, and we'll see where exactly the packet is failing, and when to check ARP, when to check CAM table, and how to compare, and to you know to leverage our troubleshooting better. And followed by that, we will take a closer look on VLAN .1 queue trunking. You guys might be heard of this. It's for tagging your traffic. That's in a trunk. We tag multiple VLANs to it. And followed by that, we will do a scenario for inter-VLAN routing. It's also called as a router on a stick. So the key difference is the inter-VLAN routing and the router on a stick. I would say that the inter-VLAN routing, we do this with MLS. We say this MLS is a multi-layer switch where you create a sub interface. We call this as not a sub interface. We call this as a logical interface, VLAN interfaces. That's not actually a physical interface. That is a logical interface that is similar to loopback, but this carries the tag, but whereas loopback is not. Loopback is a routed port, whereas here you use this for VLANs. And the router on a stick is something you tag the VLANs on the physical port with the help of sub interfaces. When people ask you the difference between the inter-VLAN routing and the router on a stick, the router on a stick is something the routing happens on the physical port that we call as a routed port, whereas the inter-VLAN communication happens on your logical VLAN ports. And right from your routing and switching, your SD-WAN, and to your firewall, VLAN is very essential, and we should understand the VLANs. So that helps for most of your troubleshooting. So there are various deployments in enterprises, but I have seen mostly the firewall. For firewalls, example, if you have your DMZ gateways on your firewall, it's your switch is just an layer 2 trunk to your firewall. So I would say you should definitely pay more attention to the inter-VLAN routing. So that actually helps for your multiple deployment scenarios in the enterprise designs and troubleshooting. And spanning tree, when coming to the spanning tree, ideally, it manages the loop by itself. We are not much tweaking the spanning trees, but when we do a troubleshooting, we will see what are all the key parameters we should understand for the spanning tree perspective. What are the key, points and the key parameters we should be aware of to understand and troubleshoot spanning tree most. But spanning tree, it actually, it's a very good very good protocol for your loop prevention, especially in your layer 2. So it does everything, but we have to understand how exactly it works, and we should be in a position to troubleshoot when there is a problem in spanning tree. So we will have a case study for it, and also we'll do a lab for that. Then the multi-switch scenario with access link and tag link, it's nothing but all the endpoints connected ports, or we call this an access port. So it carries only one VLAN. It doesn't carry multiple VLAN on it. So that is an access port. It's limited to one VLAN, whereas the tag link is a trunk link. When it is connected to the neighbor device, it carries multiple VLANs together. So followed by that, we'll talk about LACP. This is for bundling your ports. Example, if you got your 2 fiber port and each has a capacity of 10 gig, so if you bundle it together, so that becomes your 20 gig port. And that's really, I would say it's not a hack, but the switches believes that this is a single link, right? So it's a kind of hack. I mean, you bundle the ports, but still from the spanning tree perspective, it just looks a port as a single port. So that is the use of LACP. You're utilizing your bandwidth. Then that's it really. So we will go through everything one by one. So to start with, let me open the presentation for you guys. So first topic, let's first go to VLAN. Let me open a blank slide. Okay. Let me grab my pen. So in a typical deployment example, why do we need a VLAN, right? So this is a switch. Example, if you got 5 networks. Let's make it very simple. So you got 5 network, but you got only one switch, right? But for the 5 networks, I need 5 physical switches. To have my five networks hanging over here, I need 5 physical switches. But instead of that, with VLAN, VLAN stands for virtual LAN. We all know about this, but let me take a different color to differentiate here. For example, if I say 5 network, by my blue network over here, it is 10.0.0.0/8. Example, let me give a VLAN number for it, that's VLAN 10. So if I take a different color here, a red VLAN, so that is 20.0.0.0/8. So the VLAN number is VLAN 20. So instead of buying 5 different physical switches, I'm going to use one single switch, and I'm logically segmenting the ports. So this is a great cost reduction, and it's a great technology. It's just a virtual LAN. This is, I mean, you can create as many VLANs you want, and there is a limitation for it. The number in the command line, we can say it, but you can have thousands of VLANs, but practically it depends on the switch throughput. You cannot have 100 VLANs. So in the typical design, maybe they might have 30, 40 VLANs. maximum. It depends, right? So we also, this also, we have to consider your hardware capacity, and other hardware constraints actually hampers if you create multiple VLANs. But I would say in best practices, I have seen 30, 40 VLANs you can definitely run in a switch without any problem. And for every switch, the capacity varies. So we are talking about the typical traditional switches. Let me say it's 3650 Cisco device and other vendor devices, very mid-size switches. So this is VLAN, right? So why do we need this virtual LANs? Because I have a single switch, but I can run multiple VLANs into it. So that's the greatest advantage of using VLANs. And coming to that, so what is 802.1q, and what is ARP table, and what is CAM table, and what is broadcast domain, what is collision domain? There are different key points in layer 2. Let me scroll my diagram. This is very simple representation of VLAN. So we'll go VLAN by VLAN. So this PC1, this is on VLAN 20. This is a green VLAN over here. And the VLAN 10 is on the red VLAN. Both are in different network. You can see the green VLAN is on 10.0.0.2 and the red VLAN is on 11.0.0.2. So if it is a multi-layer switch and I want to create two VLANs, right? So definitely I want a gateway for this. My this network, this computer has to come over here. And my gateway would be something like that. I'm creating everything in the multi-layer switch. I'm not going to the router here. This is purely an inter-VLAN communication, right? So right over here in the switch, I create two interfaces, one for interface VLAN 20 and interface VLAN 10. So what happens here? This particular PC, this port, the green VLAN, right? This is a green VLAN and this is the red VLAN. You can give your description, but this is just for understanding. So when you do an 802.1 queue tagging over here, so this is going to say this belongs to VLAN 20, right? And I am creating a virtual interface here. This is not the router port. This is inter-VLAN communication. So I make this communication, this communication is happening between two different VLANs over the interface VLAN 20 and 10, because that is a gateway for it. So what is the inter-VLAN 20? What is the IP address I assign? Because this is an L3 VLAN. We say this is an L3 VLAN because you can assign an IP address to it. So here example, it is 10.0.0.3/8. And for interface VLAN 10, I'm going to assign an IP address 11.0.0.10/8 over here. Let me use a different color to differentiate. So for VLAN 10 red VLAN, this is the IP assignment for it. And for this guy over here, VLAN 20, green VLAN, 10.0.0.3. So I'm assigning these two IP address over here. So my VLAN communication happens between the interface VLANs, right? That is the gateway of it. So this is traditionally everybody is doing, but what we are going to learn more than this here from the troubleshooting standpoint and also from the Wireshark perspective, how we are going deeper with this to troubleshoot better, right? Because in every enterprise I have seen, there might be a problem. Most of the problem that happens with VLAN, duplicate IP address. So we will replicate a scenario. We will do a simulation for it where we will do a little bit of troubleshooting with that. So we are going to find out, is it a problem with layer 2 or it is a problem with layer 3? Say, for example, if I assign a VLAN 10 over here for this particular port, the green port, but it is supposed to be VLAN 20, right? And one more thing, very, very important. If you're creating a VLAN, this is interface VLAN 20, and this IP address is something like 10.0.0.4/8, right? Because this PC1, VLAN 20, both are in the same network range, both are in the same IP range, right? For your layer 3 communication. What if I assign an IP address something like this? If I assign an IP address something like 11.0.0.3 over here to this PC, my IP communication never works, right? Why? Because my gateway is 10.0.0.4 and it is /8. Even here it is /8. So this subnet mask plays a vital role in your IP communication. If you do something wrong with this gateway is never going to recognize this PC is coming from the same network, right? To him, it all looks with this IP. Okay, both are in same VLAN, but your IP is incorrect. Even though the VLANs or even though if you have a proper VLAN, but if you have a wrong subnet range or if you have a different network range, that's going to hamper your connection. I would say not hamper your connection, that's going to break your connection. So we have to be very, very careful in that. And how Wireshark is going to figure out and how we will find where the problem is, right? So we have a different set of filters to figure out how exactly we can find this problem. But let me give you more, understanding, and we will cover the complete fundamentals of VLANs and inter-VLAN routing. So that's subjective for now. Okay. Going back to the content. So we talked about the inter-VLAN communication. So two different VLAN. So it works like that. So the same logic, it applies to all the VLANs. You may have 30 VLANs, and if it is an inter-VLAN communication, for every VLAN, you should have your interface here. Example for your VLAN 10, for VLAN 20, VLAN 30, VLAN 40. This is 10.0.0.1, this is 20.0.0.1, this is 30.0.0.1, and this is 40.0.0.1. We discussed about ARP for sure. So we are going little fast with this ARP. So what if this PC want to talk to this IP address, to this PC2, right? So it's going to send an ARP request. So apparently it's a broadcast. Apart from this receiving port, it's going to broadcast out to all the ports, right? Apart from this green port, it's going to send in the trunk and also to this red VLAN. But for this, since this is in a different network, for this ARP request, my ARP responder would be this VLAN 10, right? It's going to tell me that, okay, you can send the packet to me. Then again, I will do an ARP request. I have the network, 20 network. It's in my routing table. I know how to route this. I'm going to send an ARP again. But now when I'm doing ARP, right, my ARP starts from here, right? So it's from VLAN 20 over here. For my ARP request from VLAN 20, it goes out to this particular port because I have only one port. The same logic applies for all the devices. If you have 10 devices, it's going to broadcast out to 10 devices. And this IP address has the MAC address what I am looking for. The whole objective of ARP is to get a destination MAC address. So for my ARP request, I'll get the MAC address and my packet will be forwarded to the PC2. Fine. So what if I have something misconfiguration happened here, and how I'm going to troubleshoot that? So where exactly I should see? So whenever there is a connection, when there is no connection for a particular destination, when you're doing from a switch, so I would recommend you to take a capture, something like this. You have to take a capture. So if I say this is an ingress, right? This is traffic coming into the switch, going through the switch, and this is an egress going out, right? So capture filter should be for both VLAN 10 and VLAN 20 here in this particular scenario. So whenever you're initiating your traffic, you have to capture your traffic for both your source VLAN as well as the destination VLAN. So here, if you see, the source VLAN is VLAN 10, that is trying to reach VLAN 20, right? This is destination VLAN. S stands for source VLAN, D stands for destination VLAN. So I want to capture traffic for both. So what should I capture? So I would suggest you capture the whole IP communication. Because we know, we discussed this in the previous classes, your layer 2 should be good. It's all your VLANs comes in layer 2. Then your IP communication layer 3. So apparently, if you capture the traffic, you should see your layer 2 and layer 3 together. So whenever you're doing a capture, the protocol what you want to define, especially for your IP communication, you have to define your IP as a protocol, and the source VLAN is VLAN 10 and destination is your VLAN 20. In some devices, you may have to give your access list where you have to define your source network and the destination network. But I would always suggest you to do IP any, but you capture a lot of traffic with this. You can filter, or if you're very sure about a particular connection, instead of giving IP any, IP any is source, the second any is for destination. But instead you can give the source as 10.0.0.2 and destination is any. This makes sense. So this actually reduces your traffic. So that depends, right? You have to be a little more creative when you're doing your troubleshooting. So it depends on how big is your production network and how many hosts it's hanging on. So you have to consider everything before you do a capture. But I would say the primary values you have to focus on is your source VLAN, your destination VLAN, and your IP protocol there. We'll see that in our capture, but I'm talking about the production network where you encounter a problem. So example, the VLAN logic, as I said, it's very, very important because The same thing, the same logic applies irrespective of any devices. I mean, if you connected your load balancer on a particular VLAN 10, it can be a firewall on VLAN 10, but your traffic is coming from a server VLAN 20, and VLAN 10 I know the VLAN 10 is for your firewall VLANs. Still, the logic is going to be the same. So what you capture is when you're trying for your IP communication, it is always better if you give IP protocol that's going to capture all your traffic. And coming back to the topics again. So now let's move to ARP table and the CAM table. The switch actually holds a different table. Let me give you again. So when we talk about switch, and if you're talking about the layer 2 switch, so the only VLAN on your layer 2 is it doesn't do inter VLAN routing because it is not routing. I mean, it is not a router, or it is not a layer 3 switch to do routing. It's not capable of routing. So if it is a layer 2 switch, the only table it has is CAM table. Also, we call this as a MAC address table. So if you run a command to check your CAM table, your MAC address table, it's going to tell us, it's not going to give us an IP detail because it's purely a layer 2 device. So you're going to check the MAC address. Example, the MAC address is AA and this is the MAC address BB, right? So it's going to show you that MAC address is AA and it is on VLAN 20 over here, right? The green VLAN. And MAC address BB, it is on VLAN 10. You will see only these two details. This is CAM table, a MAC table. It doesn't do routing. So you don't see your ARP table in the layer 2. Okay. So coming to the layer 3 switch. When I say layer 3, it does inter VLAN routing, right? And along with that, it has two tables. One is ARP table, the MAC table, or the CAM table, right? So what should I see inside the ARP table? The IP address and the corresponding MAC address to it. So this is AA and this is BB. In the MAC address table, only I can see the VLAN tag to it. But in the ARP table, I can see 10.0.0.2 and along with that, the corresponding MAC address to it. It's AA, right? You give show IP ARP or show ARP. It depends on the platform, but the logic is going to be same. So for 11.0.0.2 and my both interface VLAN hanging over here, right, on this particular switch. So that is 11.0.0.2 on the MAC address is BB. For my successful IP communication, I need MAC detail and I need an IP address. I need source IP, I need a source MAC, I need a destination IP address and the destination MAC. So once I got all the four values, only then I can establish a connection to it. So we all know this, but I'm trying to emphasize this to, get better understanding, because this is very, very important for your troubleshooting. So if you don't see your ARP table, so it means that the PC1 is sending an ARP request, but the PC2 is not sending an ARP reply back. It could be it could be a wrong IP assignment, it could be a wrong VLAN tagging, or it can be a trunk is not forwarding your traffic, or your inter-VLAN communication is not happening, or it can be your ACL. So before that, the fundamental communication is I need four key parameters for my successful connection between PC-A and PC-B, or we can say PC-1 to PC-2. So let's do a lab. We will understand better. So yeah, this is about the foundation topics for theory. So how this inter-VLAN exactly works, and what are the key values we should look into the layer 2. And when we talk about the 802.1q, it is an header in your layer 2. That is called tagging, right? So where the source traffic is coming from. Just a minute, let me log into my RDP. Okay, so let me open the capture. 1 minute, let me reshare again. Okay. Let me take this. Okay. So if you see your layer 2, let me quickly take the pen. Okay. So if you look at this, this is VLAN 10, right? So this is the header. It is appended into your layer 2. So if you see this, you can see your source MAC address, your destination MAC address, and this is a separate header. It is 802.1q virtual LAN, and if you can see your ID VLAN 10 right over here, right? You can see the VLAN 10 over here. So we are actually establishing an IP communication, but also we can see the layer 2 header. So when you're sending an information, it will show your source VLAN as well as your destination VLAN. So this is coming from 10.0.0.10. and you can see the source VLAN is 10, right? If I go to the destination and if I right click on it, if I do apply as a filter and if I do select, it will show all my IP packets here. So when you see the source over here, it's 10.0.0.10 and it's coming from VLAN 10. I tagged for all the 10 networks, I tagged VLAN 10. If you look at this 10.0.0.1, it's coming from 10.10 VLAN 10. But if you see the MAC address, right? If you see the source MAC address, this is 6804. Whereas if you see over here, this is AB00. So both are coming from a different, you can see this, right? If you see, this is the MAC address. This is the MAC address of 10.0.0.10 and VLAN 10. And if I go back to 10.0.0.1, the MAC address is different, 6804, but the VLAN is 10. So it is a separate IP header. From this, it's going to differentiate from which VLAN it's coming in and what is the destination VLAN I have to send to, right? Fine. So let's again go back to the PowerPoint. So what exactly it looks like here in the actual devices? So access port can carry only one VLAN information, right? So all this access port, this particular port, green VLAN is assigned for VLAN 10, and this is a VLAN 20, and this is VLAN 30. And as I said, you should have your interface VLAN here for all the VLANs, right? With IP address. Example here for interface VLAN 10 for 10.0.0.0, and for interface VLAN 20, it's 20.0.0.0, and for interface VLAN 30, it's 30.0.0.1. Here 20.0.0.1, and this is 10.0.0.1. So you should have 3 interface VLAN. Only then your routing happens, because all this interface VLAN has an IP address. So all this VLAN, right, without an IP address, just with tagging, right, ID 30, we call this as layer 2 VLAN. In most of the scenarios I have seen, we create interface VLAN, but we never do the layer 2 VLAN, but your communication is not going to happen. Because you got your gateway, you got your IP address, but the endpoint coming from has to be properly tagged, and the switch should understand, okay, the traffic is coming from VLAN 20. So the other vendor devices, actually, I'm not fortunate to use it, but in Cisco, I have seen when you're creating just an access port without creating a VLAN, a layer 2 VLAN, it creates a VLAN automatically when you're creating an access port. It's going to give a warning that VLAN 20 doesn't exist, but the VLAN 20 is created. The layer 2 VLAN will be created, but not the layer 3 VLANs. Only the layer 2 VLANs are created automatically when you define a specific port, when you configure a specific port for access port. So then what is trunk? If you see, all this access port is carrying only one VLAN per port. But when you see the trunk port over here, it carries multiple VLAN. That is called a tag port. So for vendor to vendor, it differs, but the logic again remains the same. If you do a trunk between that, we call this as an uplink connection, right? We call this as an uplink connection. You can call this either way. From this switch, you can call this as a downlink connection, but the whole logic is you have to tag your VLANs only, then your VLANs will be spanned across VLANs. Because if you look at here, I got VLAN 10, 20, and 30, and also on the switch 2, I got VLAN 10, 20, and 30. And if I do a trunk and if I allow all these VLANs, only then my VLAN communication happens. Say, for example, here in a port in VLAN 30, it's coming in, and if I didn't tag the VLAN 30, this particular wheel traffic, right, from the switch over here, it's trying to talk to the, a device which is connected to this particular port on VLAN 30. But since you're not sending any layer 2 VLANs, then how this communication happens? So your communication is going to drop, because in the trunk port, I don't see the VLAN 30 coming in to me. So when you are doing a troubleshooting, the end-to-end connection, you have to be very sure whether you have created your layer 2 VLAN properly and you have your layer 3 VLAN properly configured. So that's it really about inter-VLAN communication. We covered all the we covered all the parameters, and I would say we covered all the necessary information what we need to understand for inter-VLAN communication. Okay, so coming back to this, we talked about .1 queue, and we are going for inter-VLAN communication router on a switch. So as I said, let me take this. Okay, fine. So let's think this is a router and this is the switch, and you got a couple of computers connected to it, and you have a connection. So A stands for access port, carries only one VLAN. So where the switch in the multi-layer switch, it was doing inter-VLAN communication, but we call this a router as a stick because we are using the switch as a pure layer 2. It's not doing any routing. When we jump back here, the different color here. Okay, so this is on VLAN 10, this is on VLAN 20, and this is on VLAN 30. So we have 3 layer 2 VLAN. What are they? VLAN 10, 20, 30. So over this trunk port, right, I'm going to tag VLAN 10, 20, and 30. No IP communication happens on the switch. So how does this router is going to respond, and what should I do in the router to establish a connection between different VLAN here? So as I said, this is a physical port. You can give a naming convention, something like it's a gig port 1/2, and on the switch it is a gig port 1/3, right? So I made this port as a trunk on the switch. You see the red line over here, the red dot. So I made this particular port as a configuration as a trunk. So it means that I'm going to allow, it's an open VLAN. I allowed all the VLANs. So it means that this particular trunk port is carrying VLAN 10, 20, and 30. It's a pure layer 2, and it goes to this router. And this is called a router on a stick. And this is a routed port because this is gig 1/2. But here is a challenge, right? So I got only one physical port, but how I'm going to do a routing for multiple VLANs? So then again, so in the router, we have a feature called as a sub interface. You can call this as a logical interface, but the best definition would be the sub interface. So GI 1/2 dot 10. So my actual interface is GI 1/2, and I'm logically creating an interface as .10 for better identification. That's how you can differentiate. Okay, this gateway is for VLAN 10. And for GI 1/2, VLAN 20. If you look at this, the first two values remains the same, GI 1/2. I didn't change it. Only after that dot, I am creating the interfaces, sub interfaces, followed by that GI 1/3.30. So now how I can do a tagging in the routed port in the sub interfaces. You have to go to the every single sub interface and you have to define encapsulation .1Q VLAN 10. The same command for encapsulation .1Q VLAN 20. It goes, you can create as many VLANs you want. I mean, as I said, there is a range from 1 to 4,000, I believe. But as I said, in the production environment, it never, shoots up to 70 or 100 VLANs because the throughput and the capacity of the hardware, you cannot do that. That's not the best practice. But you can say for example, you have run multiple VLANs, as many VLANs as you want, up to 30, 40 VLANs. So for every VLAN, you have to have your sub interfaces created, and you have to enable the encapsulation .1Q command. That's something you're telling that this particular interface GI 1/2 belongs to VLAN 10. I am tagging for VLAN 10. So whatever the traffic coming to the router, it hits actually to this particular interface, GI 1/2.10. And after assigning this is for VLAN tagging. After assigning this, apparently you have to assign the IP details along with that. Example here in VLAN 10, 10.0.0.1, and in VLAN 20, it is 20.0.0.2, and in VLAN 30, it is 30.0.0.3. So the same logic, if a traffic coming from VLAN 10 and it wants and it has to talk to VLAN 20, it is not east-west traffic. It is a northbound connection. When I say northbound, from bottom to top, it goes right over here. It goes to this gateway and it routed back to VLAN 20, and it comes back again to VLAN 20 over here. This all happens here in the northbound. It hits your router and comes back to the switch over the trunk, and from the trunk, it again goes to your access port. That's your flow of traffic. So same logic in the switch, in the multi-layer switch, you have interface VLANs, but in the router, in the physical port, you create multiple sub-interfaces and you are doing your routing. But the mechanism, both are same, no change. So coming back to the spanning tree. So I would say spanning tree will more focus on troubleshooting, but spanning tree, instead of going for the bigger topology, I would always suggest understand the smaller topology. That's very important. And along with that, irrespective of if you resize your network, if you resize your network into a big network or it can be a mid-sized network, the logical remains absolutely same, no difference. So why do we need a spanning tree? That's the first question, right? Why do we need a spanning tree? Without spanning tree, what really happens? So example, if there is no spanning tree, if you look at here, this particular port is blocked by the spanning tree. If there is no spanning tree, what exactly happens? A traffic from the switch A is going to the switch C over here, hanging over here, right? To this computer from here, left to right, the east-west traffic. If you follow this dotted lines to your right-hand side over here, right to the corner. So your actual traffic, if it is something like this, so it may go to this path and also it may go to this, right? It can prefer both. It can go through this link as well as this secondary link over here. So what happens here? It's a loop, right? So when the response is coming back, it will send to the switch A and also it will send the reply to the switch C. So the traffic comes through the switch C as well as it comes through the switch A. So it's like a loop. It's called as a broadcast strong. We will see what exactly happens if you disable the spanning tree. And the most vendor devices spanning tree is enabled by default. So coming to the logic of and the mechanism of spanning tree. So for the spanning tree, there is always one root switch. So in the legacy standards back in 2010, 27, I mean, this has recently changed. I don't remember exactly when they changed the naming convention, but now it is actually changed as STP root. It's we call this as a root bridge, but the logic again that remains the same. This spanning tree protocol, this is non-root over here. All the two devices, there can be, it's a best practice always you should have one root bridge. So right away you guys might be thinking how exactly it's used in the enterprise. Yeah, absolutely. Your core switch or maybe all your VLANs is hanging over your core switches, right? So it's always your core switch is your root bridge. So the root bridge ports are always a designated port. Let me circle this. All your designated ports. Whenever you see your root bridge, the ports are always designated ports. It means that the port is open, the communication is happening actively, there is no block. So when you actually connect a device something like this, when you do a cabling from switch A to switch B and switch A to switch C, and you have a connection exactly in the same way when you try to do it, it's going to block one port. But the next question is why it is blocking this particular port and not this. So this is purely based on the path cost. Example for the fast Ethernet, it's something I think it's 19. So for this switch A to reach this particular port, it's a 19 plus 19, right? When you add this together, that's the actual value. So it thinks that, okay, this is the longest way. So I don't prefer this. So the shortest path, and this device is very close to me, and I'm going to prefer this link as my designated port. And your port facing your root bridge, your root switch is always your root port. And what if the cost value is same? If I have something like this one more switch over here, and if you have an interconnect like this, the path cost is same. It's going to prefer the least port ID. Example, if this is fast Ethernet 0/3 and this is fast Ethernet 0/1, this is going to prefer this. Don't worry much about this spanning tree. Everything, that's more like an automated process. We are not doing much manual configuration to it, but I want you guys to understand how exactly the election happens. And not only with this, right? I mean, we talked about root port, we talked about designated port, and if you actually see the priority value 32769 is common for every device, and how this root bridge is elected. So every device is going to send a BPDU value, bridge protocol data unit. We say the BPDU packet contains your priority and your MAC address combined together. So it's going to calculate who has, if you look at the priority for this particular example, the priority is same for all the three devices, but only the MAC address is different. So it's going to prefer the BPDU with the lowest MAC address, because the tiebreaker is the priority remains the same. So this A1 is the lowest MAC address compared to BB1 and CC1. So this is preferred as a root. But what if I have a device, it has the highest MAC address, but I want to make this as a, if I want to make this particular switch A, even though it has the highest MAC address, but I want to change this as a root bridge because that is my core switch. You can tweak. You can tweak the priority. The least priority is preferred again. So if you change your priority to 32760 something like that, and if all the other devices are 32769, so the least priority is preferred here. Least is preferred in the spanning tree election. And apart from this, whenever there is a changes, right? If you create your VLANs and if there is any changes in your spanning tree, every single time it's going to send the TCN notification, topology change notification. Example, if you do some changes to this particular switch, it's going to say that there is a change in your topology, and this TCN notification is sent across all the links. So here is a question. So this port is blocking, but this is listening. So when I talk about the port states in spanning tree, that is very important. The port states are learning, listening, and forwarding. So this blocking port is actually listening. Why it is listening? If something happens to this particular port, this port becomes an active. It continuously, forward the traffic. Only if this link goes down over here. So this blocking port is always in the learning state. Sorry, not always in the listening state. The root port is always in the forwarding state. And what about the learning state? So whenever you connect your end devices, there's something called as port fast. Because this is not involved in any kind of STP election process, because this is just an end computer. So instead of these two states is combined together, and it will go right away to your forwarding state when you enable the port fast. And the port fast command is recommended, and only it should be used on the endpoint ports, not in the trunk ports. So that is about the spanning tree. And one more thing, I missed that. Yep. Followed by that, the spanning tree mode. There are different types of spanning tree modes. But what we are going to cover today and the mostly used is PVST, and it is plus. Plus stands for the Cisco proprietary. That's not a big difference. It's more similar like an open standard. Open standard is PVST, and Cisco and made this as a PVSTP plus, and they fine tuned something like a system ID. Don't want to focus much on that, but per VLAN spanning tree. So what happens for every VLAN? So for VLAN 10, for VLAN 20, if you got two VLANs, per VLAN, there is a spanning tree process is happening. Example for this STP root bridge is a root bridge for VLAN 10. But this guy over here, switch B, can be a root bridge for VLAN 20. But that is not recommended again. So per VLAN spanning tree, whatever the spanning tree you run, but it is always good to have one single root bridge that avoids your confusion, and that's actually the best practice. So per VLAN, it runs a spanning tree. So for VLAN 10, this guy can be a root. For VLAN 20, this guy can be a root. That's again to different to make to give a difference. I just said this, but actually it is always better and the best practice is always to have one single root bridge for all the VLANs you have in your device. So what we are running is a per VLAN spanning tree in this particular topology. So when you turn up your port, if it goes to the blocking state, listening state, learning, and forwarding. And the bridge ID, if you see the bridge priority and the MAC address. When a port on a switch brought online, it goes through a series of spanning tree port states. These states change in a predictable pattern based on the information derived from the BPDU received on the port. As I said, in the port fast, if it is for the endpoint devices, it listening and learning and listening combines together, and it goes right away into a forwarding state that produces somewhere around the 30 seconds faster than your normal spanning tree transition. So you should enable port fast and BPD got to the ports connected to the end host only. As I said, that's the best practice, because BPD got, because this computer is not a switch to send the BPDUs, and it is never, it is not necessarily, it should be a BPDU device to participate in the election, because this device is an endpoint device. It's just going to send a traffic for one particular VLAN, and this is not doing anything else apart from the IP communication and other stuff, and it is not involved for your actual spanning tree process. You can configure the uplink fast and switch C, example in this scenario, so that the blocking port can transition into the forwarding state faster when the root port fails. So when you enable your uplink fast on this, what happens? So example, if it waits for 50 seconds, it's just going to wait for 20 seconds, and it in the transition, it transits from it transition from the blocking state to forwarding state. So that happens quickly when you enable a uplink fast command on this. This is all something to reduce your convergence time. So spanning tree best practices, always configure a root bridge. In production network, the position of the root bridge is critical for optimizing traffic flow. Don't let the spanning tree choose the root bridge on its own. As I said, sometimes if it prefers its own root bridge, it's a problem again. So always your core switch or your central switch should be, your core switch should always be your root bridge. Choose which switch in your network will be the root and give it a bridge priority of 1, because the least is preferred. If you give 1, that becomes your root bridge. If you let the switches choose, they may not choose one. That makes no sense. Switches added later may also assume the role of the root bridge. As the network discovers path to the new root bridge, the entire network will reconverge and the links will change the state. So we have to be very careful when you're adding your new devices, or maybe if you're replacing your existing devices with the new devices in your network. So these are all the couple of commands you can run to check. We can do this in the lab. Other possible loop contributions are, it can be a duplex mismatch, UDLD, it's out of topic again, unidirectional link problems. It happens with your fiber ports, fiber cables. You got actually basically if you have, it has RX and TX, right? You guys seen the optical cables, you might seen this. You got RX and TX, one for receiving traffic and one for transmitting traffic. If one port goes down, still it is a problem, right? So that is called unidirectional link problems. It's out of scope. Again, you're giving a little more little background about that. And the switch resource problem, or it's if your CPU is too high and it is running some other process, it can also be a problem for the loop. Example, if you connect, if you disable your spanning tree, if you disable your spanning tree, that spikes your CPU. I meant that switch resource problem. And incorrect port fast configuration, if you configure your trunk port as a port fast, so it is potentially, it impacts your spanning tree process. Incorrect BPDU filter, if you apply this to your trunk again, this should be only for the endpoint. And if you do a BPDU filter, then what happens, that particular switch will never participate, and it never been elected as a root, or never been sending the BPDUs, and apparently it will never participate in the election. So that may be a problem for your loops. So you have to be very careful in BPDU filters where to apply. So incorrect disabling of STP, physically connected loop, software errors, STP mode switch mismatch. Example, if you have your switch over here, if you have your switch with PVST plus, and if you have something like MST, multiple spanning tree protocol, and this is not recommended. You should always run the same spanning tree protocol on both switches. STP modes mismatch between switches in the same network can potentially create a loop. So ensure that you should always run the same spanning tree protocol on all the devices across your network. So when you see in the production network, this is how exactly we do this, all the access ports or all the end devices connected to it, and all the switches are connected as a trunk because it carries multiple VLANs for your inter-VLAN communication. So T stands for trunk port. Example, if you see here, we got VLAN 10, 20, and 30 right over here, VLAN 10, 20, and 30. On all these ports are capable of carrying only one VLAN. We discussed about that. And in the trunk ports can carry multiple VLANs, and it's a trunk port. So this is a simple example for it, how the trunk, where we have to configure the trunk, and the untagged is an access port. You have to connect, you have to use this for your endpoints. That's it. Then I think we can do a lab. Then if we have time, then we will jump back again to the LACP. Now let's do .1Q trunking, your inter-VLAN communication, and we'll do access port and the trunk port. So if you look at this, very simple topology. So I created interface VLAN 10 and I assigned 10.0.0.16 for switch 2. And if you see for this PC, I assigned 10.10.0.0.1/16. And I assigned 10.0.0.1/8 VLAN 10 for switch 1. And if you see, this is all the designated port. And the port facing your root bridge is always your root port. So from switch 3, for switch 1 is the root bridge here because it got the least MAC address. So the port fast Ethernet 1/4 goes to the root bridge 1/4. So this is a router, a root port. Again, the switch to fast Ethernet 1/2 goes to fast Ethernet 1/3. That is again a root port, and this is a root bridge. And if you see, even in the blocking ports, it sends a BPDU here. And I got one more trunk in this topology where we configure the LACP but now for the spanning tree in the inter-VLAN communication, we are going to use the topology over here. If you bisect in the half of it, so we are just focusing now only on this particular lab, only the devices switch 2, switch 1, switch 3, and this VPC, not switch 5, switch 6, and VPC. This is not used for this particular lab. We cancel this. I think I have an session open already for all this. So if I go to this switch, so first we will talk about spanning tree, followed by that we'll talk about the inter-VLAN communication. Then we will have a router with router on a stick. So if I show you the VLAN, so show VLAN switch. So if you look at this, so VLAN 1 is a native VLAN. We all know that VLAN 1 is a native VLAN. So all the ports are assigned to VLAN 1 by default. It's not tagged. So if it is not tagged, even though if it's just, all the ports are in VLAN 1 and you don't want to actually tag anything because by default it is untagged. VLAN 1 is untagged. So if you send a packet from VLAN 1, you can't see anything. It just shows a VLAN 1 for everything, even though if you're not doing a VLAN 1 config access port VLAN 1 on a particular port. Example here, if I go to fast Ethernet 1/4, it is not necessarily I should give a switch port mode access VLAN 1. By default, it is on VLAN 1. So I created VLAN 10 and VLAN 20 over here in the switch. And the switch is not connected to any end devices. So it is just a trunk for this VLAN. So it says that the VLAN 10 is active, VLAN 20 is active. And again, this is a layer 2 VLAN, right? This is a layer 2 VLAN, L2 VLAN. It doesn't have any IP address on it. So I got VLAN 10 and 20 here. Let me grab the pen. VLAN 10 and 20 on switch 1. And if I go to switch 2, if I give show VLAN switch, the same thing over here, you can see VLAN 10 and 20. On switch 2, I got VLAN 10 and VLAN 20. Again on switch 2, the same thing on switch 3. Okay, so when I say the per VLAN spanning tree, so it's going to run a no spanning tree for 2 VLANs for my VLAN 10 and 20, right? My PVST for both VLANs now. PVST for VLAN 10 and PVST for VLAN 20. So this port is blocked. So how do I check? If I go to switch 2, show spanning tree block ports. Let me give show run interface fast Ethernet 1/6 over here. That goes to this connection is for switch 2 and switch 3. Show spanning tree. Let me go to the first option. Okay. So for VLAN 10, so it as I said, it's running spanning tree per VLAN spanning tree. If you see for VLAN 20, I see the spanning tree, and the root bridge, it is telling that the root switch is this guy, right? 0.0.0.2. And if you look at this is the MAC address of this particular device. So we are on switch 2. So this is the MAC address of the switch. How do you check? If you give show version, then show IP interface brief. Show MAC VLAN 10. Show spanning tree brief. So we are on switch 1. 1 minute. Let me quickly check this. We are on switch 2 over here, and it's telling that 44AB00 is my bridge, right? This is the MAC address over here. I cannot scroll this. Okay, so the bridge ID is the MAC address of that particular device, and this is the MAC address of root ID over here. If you go, you can check that actually. If you go to the spanning tree, you can see show spanning tree brief. You can see this MAC address, right? 53F2. This is the root ID and the bridge ID. Both remains the same, right? So the bridge ID belongs to the MAC address of that particular switch, and the root ID is the root bridge. So both are same. So this particular switch 1 is the root bridge for this topology. And if you go and check in the switch 2, you should apparently see the root ID is the MAC address of switch 1. And if you go to the switch 3, If you actually see this port 1/5, right? If you see port 1/5 and port 1/5 and port 1/6, both are in blocking state. That is expected to prevent the loop. So this guy over here, he's actually in the forwarding state. If you jump back to the switch to port 1/6 and port 1/3, both are in forwarding state. So that's but the interface and the remote interface 1/6 and 1/5 both are in blocking state here. You can see 1/6 in blocking state, 1/5 is blocking state. We haven't done anything. It is by default. So how the selection happened? So everybody they propagated their BPDU. They shared their BPDU, and the device with the lowest MAC address is elected as a root bridge. And we know this is a root port, and the root port is always in the forwarding state. And you can see the port cast over here. For fast Ethernet, it is 19. So as I said, the port cast from here, it's 19. Let me take my pen. So it is a 19 over here. It's again 19 over here. So this is the longest path to reach over here. So this particular port is selected as the root port because the cost for to reach over here is less compared to the switch tree. As I said, we are not doing much with the spanning tree. This is just we are understanding the mechanism of spanning tree, how it's blocking the port, and how we are going to troubleshoot it. Okay, show spanning tree brief. So show spanning tree brief will give you the complete port details. Is it in a learning state and or forwarding state, or it's in a blocking state? And along with that, it will give you who is the root for VLANs. And as we discussed, it's a per VLAN spanning tree. So for every VLAN, it's going to show who is the root and who is the bridge. So bridge is local device, and the root bridge is the actual root bridge of the particular spanning tree topology. So if I give show spanning tree VLAN 10, so this is used for troubleshooting standpoint. Let me make this a little bigger. Okay, if you see this number of topology change notification 1, so it occurred exactly 1 hour 44 minutes ago. So this is very important when you're troubleshooting, right? When you're troubleshooting, your spanning tree is expected to be stable for even for 2 days once, 3 days once. If something you're making changes to your switcher VLANs, we know that in the enterprise devices we don't do much changes, but if you do some changes, it should be some meaningful value. If it is flapping every 30 seconds, 10 seconds, that's something you have to look why this topology change is happening and who is sending this topology changes. So actually, if you see the number of topology changes has happened in 1 hour ago, the total topology changes is 35. So these are all the key values you should see. So I'm doing this only for VLAN 10, right? If I do show spanning tree VLAN 1, Again, the VLAN 1 is active, right? This is the default VLAN. You can see the same thing over here. So this is per VLAN spanning tree. So spanning tree is running for all the VLANs. So when you're doing troubleshooting, as I said, you have to keep your eye on this particular value, when exactly your topology change happened. And if it is very frequently happening, like every five minutes and every 5 minutes to 10 minutes, I would say you should look your spanning tree topology. Is it stable or something is flapping, and why that continuously happens? So for fast Ethernet 1/5, I am on switch 3, and fast Ethernet 1/5 is telling that VLAN 1 is blocking, because even for VLAN 1 it's not sending any messages. But if you see the BPDU messages right over here, it is still sending the BPDUs, and it is receiving the BPDUs, but it's still in blocking state, so it is in listening state. So because if the primary port goes down, the root port goes down, so automatically this port becomes an active and this becomes a root port, because we have no other option to reach switch. If we lose this link over here, the switch has only one link over here to talk to switch 1. If this primary trunk over here faster than at 0/1, if this goes down, so this is the only way I can reach to switch 1, right? So this is the, as I said, the spanning tree, everything, it happens by itself. So only the key things you have to do is show spanning tree per VLAN. You can check for your topology changes, and if show spanning tree brief will give you all the blocking ports and the forwarding ports. So if this device, and if this is the device and it's connected to the switch, and if you have a redundancy, something like this, you should ensure that always your root port is forwarding state. Your root port are always in the forwarding state, as we checked before. You should ensure that all your root ports should be in forwarding state. Only then your VLAN traffic will be spanned across. And coming to the 802.1 queue. Okay, we'll talk about ARP table and CAM table. We haven't seen that practically, how it looks. So if I give show MAC VLAN 10, I want to little traffic. I have to generate some traffic here. If I try to reach this guy over here, 10.0.0.1, I'm trying to generate a traffic from this device connected to this switch 2 to generate some traffic to see the MAC address of it. Because what happens here, when I ping this, the traffic apparently comes over here, fast Ethernet 1/4. I think I'm on the wrong switch. Show MAC VLAN 10. You see, this is the MAC address, right? This is on VLAN 10. And if you go to this particular device, right, the VPC over here, 6804. I'm looking at the wrong MAC address. Um, I'm in the switch to show interface fast Ethernet 1/4. So the VPC over here, show IP IP address is 10.0.0.1/16 and the gateway is 10 and this is the MAC address 6804. If I try to ping this guy on the switch 1, right? So let me go to switch 1. Purposely I did duplicate IP address. I'll talk about that. Show IP interface brief, exclude unassigned. Give me only this IP address over here. Okay. So if I do ping this guy, source VLAN 10, come back here, go to switch 2, show MAC VLAN 10. I think it's a bug. Let me bounce this port fast Ethernet 1/4. I'm on switch 2 over here. I'm trying to see the MAC address of this VPC. I do shut, no shut. And from the switch 2, trying to ping this VPC. Show MAC VLAN 10. I see the trunk coming in from here, this particular switch. I learned the MAC address dynamically. And this is a self VLAN 10. But I don't see any traffic from faster than 1/4. Okay, so let's take this example. So this traffic, this is coming from the port fast Ethernet 0/2 to this particular switch. I'm trying to learn the MAC address of this particular interface over port 1/2 over here. This is called as a CAM table. Or you can call this as a MAC table. As I said, the key values you should see, you will see only the VLAN associated to the MAC address. So I am learning this MAC address. I am learning this MAC address on port 1/2 over here, the trunk port. So this is the MAC address of this particular switch interface fast Ethernet 1/3. If I go and run show MAC VLAN 10. So if you see, this is the MAC address of the switch itself. It says itself. We go back to switch 2. I can see the same MAC address. I learned this from port 1/2. So now let's go to the switch 1. Show IP interface brief, exclude unassigned. Will give me only the VLAN 10. Okay, so what if I create interface VLAN 20, IP address 20.0.0.2, 255.0.0.0. No shutdown. So if you see, the line protocol came up. Line and link protocol should be up. Show IP interface brief. Exclude unassigned. So the status and protocol both should be up. And if I try to ping 20.0.0.2, I can ping. And if I do traffic sourcing from VLAN 10, I can ping. So my inter-VLAN communication happens. As I said, we got VLAN 10 and VLAN 20 coming from a different VLAN. But let's see, jump back to the packet capture and we'll see how this packet is, interpreted in the Wireshark. So if I go to switch 1, if I capture on port 1/3, let me go back and show you exactly I'm trying to achieve here. So if you look at this, I'm trying to capture a traffic on port 1/3 over here. 1/3 on switch 1. So I'm trying to ping from this VLAN 10, the interface VLAN 10 to this interface. I'm trying to establish a connection between these two. Interface VLAN 10, the traffic has to go through the trunk and it should reach switch 1, interface VLAN 10. And we should apparently see the VLANs tagged to it, right? Let's go back to the topology again. So I am coming from 10.0.0.10 to 10.0.0.1. So we generated a ICMP traffic. Go back, minimize the Wireshark. Let's keep like this. Okay, so the traffic coming from 10.0.0.10 over here to 10.0.0.1. If I open this ICMP packet, you can see the traffic coming from 10.0.0.10 to let me make it a little bigger. So the traffic coming from 10.0.0.10 to destination 10.0.0.1. And if you see the layer 2 packet, I can see the traffic coming from VLAN 10. And for this, I'll capture only this conversation filter IPv4. So 10.0.0.1 is sending an ICMP reply to 10.0.0.10 to this guy. From here 10.0.0.1 switch 1 sending a traffic to switch 2. So what do you see? Again, I tag the VLAN 10 traffic, so the communication is happening. Yeah, this is inter-VLAN communication. Also, we established a connection between 10 and 20. This is in the same switch. Let me try to generate a traffic from this guy 10.0.0.10 to the 20 network over here in switch 1. So this is switch 1 20.0.0.2. So if I go back here, till the packet capture is running, fine. The VPC is the guy over here, 10.0.0.10. Okay, so we'll do a traffic capture from the switch. This would be better. So if I go to capture and fast Ethernet 0/2 is my trunk. Fast Ethernet 1/2 is my trunk port. I'm trying to open a capture on it. Come on, it's a bit slow. So let's minimize this. Let me generate a traffic from switch 1, switch 2 to switch 1. Okay. So I am on switch 2. If I give show IP interface brief, exclude unassigned. So I got VLAN 10, and in switch 2 I got VLAN 20. So I'm going to switch to, if I do a ping to 20.0.0.2. Okay, I cannot ping. If I do show interface trunk, so apparently I should allow VLAN 10 and 20 on port 1/2 over here. So this is allowed. 1, 10 and 20 is allowed. And if I give show VLAN, show VLAN switch, so VLAN 20 is allowed, but there's no port configured for VLAN 20. I want to check the interface status of it. In VLAN 20, yeah, the port and link status both are up. I'm trying to send a traffic, but I cannot reach. So my capture is running over here. So it is telling that my originating traffic is only 1. Let me stop this capture. All my PVST, I don't see any VLANs going across. What if I try to ping this guy 10 show IP interface brief, exclude unassigned 10.0.0.1 to test a connection is that my traffic is going through VLAN 10. Coming back again to switch 2. I'm on switch 2. I can ping. If I do an ARP, I don't see any ARP packet over here. Let me do a capture again. Capture on fast Ethernet 1/2. So I see the ping packet from 10.00.10. Show IP interface brief. Exclude unassigned. So my traffic is going from 10.002 to 10.001, but whereas my VLAN 20 traffic is not going through from here. So what if I configured one more interface VLAN 20 IP address 20.00 IP address 20.00.10 255.255.00. So show IP interface brief, exclude unassigned. Let me try to ping 20.00.10 source VLAN 10. I can ping. The inter-VLAN communication is happening between these two VLANs. The what if I try to reach 20.002 from switch 2? We know, right? I mean, from switch 2, when I say from switch 2, we are trying from switch 2 to switch 1. So ping guy over here 20.002 from source VLAN 20. Now I can ping VLAN 20 to VLAN 20, right? So if you look at VLAN 20, the source from, let me little bit minimize this guy. So 20.002 is switch 20.002 is switch 1, this guy over here. So source is 20.00.10, switch 2, and 20.002 is switch 1. So switch 2 trying to talk to switch 1, and I see VLAN 10. Sorry, VLAN 20 for it. But when I try to establish a connection on port, on the VLAN 10, from VLAN 10, I can ping now. So if I drill down, I should apparently see this traffic. So the very first traffic, right? So it is telling that ARP request. So I'm trying to reach 20.002, but if you actually see the ARP request or the ARP response, it's happening in the same subnet, because it's trying to reach a different subnet. But if you see the ICMP packets 10.0.0.1, it's coming from VLAN. It's trying to reach VLAN 10. And it's coming from VLAN 20, right? So the 20.0.0.2, it's on VLAN 20, and 10.0.0.10 is on VLAN 10. So when you actually trace this MAC address, the associated MAC address and the IP address, you would see exactly, you will get your VLAN IDs there. So you can drill down and you see the VLANs over here. So now the connection is fine. So the very first thing when I try to ping, the very first packet is ARP. So I should get an ARP and ARP response back for my IP communication here. And your VLAN configuration should be perfect, and your trunk should be perfect, and your access port should be perfect. Only then your communication happens. I go to conversation filter. If I do ARP, you can actually see that we discussed ARP multiple times, just showing you the ARP packets again. So for every ARP request, you should get an ARP reply. So it's trying to reach 20.0.0.2, and I got the MAC address for it, and it's trying for the MAC address of 10.0.0.10, and it is telling that 10.0.0.10 is this particular MAC address. And you can see the VLAN tagging perfectly in the ARP here. So the 20.0.0.2 is on VLAN 20, and this is on VLAN 10. So your inter-VLAN communication is happening perfectly. So for both sources, both are in different VLANs, but still your communication is happening. So this is inter-VLAN communication. For that, first thing, your ARP should be perfect. Your routing should be perfect. Your VLAN tagging should be perfect. Your trunk should be perfect. So if you have everything properly configured, everything is in place, then your connection should be successful. That's it really about the inter-VLAN communication and the spanning tree. Let me stop this. So guys, if you have any questions, you can ask me. We are good today?
Yes.
Okay. Cool. If you guys have any questions, you can ask me. Okay. So you guys understood about spanning tree and inter-VLAN communication today?
Yes,
Okay.
Praveen.
Okay. Thank you, Deepa. Thank you, Nilofer, right? Sorry if I'm mispronouncing your
It's
name.
Nilofer.
Nilofer, okay. So you understood about spanning tree and inter-VLAN communication?
Yes, I understood. Thank you.
Okay, no problem. So guys, if there is no further questions, then we can wrap up this call. Okay, so good night, everybody. So we'll meet tomorrow. Thank you for your time today. Bye.